Hello everyone, in this tutorial I want to show you how Houdini and Unreal Engine can be combined into a single procedural environment workflow. It is intended for users with a basic understanding of both Houdini and Unreal Engine interfaces and core workflows. Before I begin, I want to briefly talk about the concept of building content across multiple applications. There are two major challenges to consider. First, every DCC software has its own way of representing data. Second, we need to find a reliable way to transfer the data between applications without losing flexibility. To address these challenges, technologies such Houdini Engine, Universal Scene Description, Unreal Engine's PCG framework allow us to preserve procedural data much deeper into the pipeline. Instead of transferring only finished geometry, we can transfer attributes, information, and scene structure directly between software. This enables a pipeline where Houdini remains responsible for procedural content creation and Unreal Engine is responsible for environment assembly, visualization, and final rendering. By the end of this tutorial, you will understand the basics of building procedural workflow in Houdini in Solaris context, how to transfer points and attributes into Unreal Engine's PCG framework, and use that data to drive procedural scattering and modular environment generation. It is equally valuable for both cinematic production and game development, from early prototyping stages to the final assembly. Okay, now that I understand the general idea, let's build a simple example from scratch. I will start inside Unreal Engine 5.4 and above. The first thing we need is support for USD and PCG, so let's enable both plugins. For this tutorial, we will use a USD stage actor to roll our scene. Unlike traditional import workflows, the stage actor references a USD file directly from disk, allowing us to update and reload data without re-importing. The same idea applies to our PCG graph. Let's create an empty one. To load our point cloud, we will be using an Alembic format. As you can see, load Alembic node also references a file directly from disk. With that in mind, let's jump into Houdini and create those files. I won't be covering all the details of how to work in Houdini. I just want to show you how you can utilize this workflow and create something unique yourself. Don't worry, I will show everything step by step. You can still follow along. Since our final goal is to export USD, I will be working directly inside the Solaris context from the beginning. I will start by creating two subgrade nodes. The first one will contain our environment geometry, and the second one will contain the point cloud that we will later export as Alembic and use inside Unreal's PCG framework. Inside the first node, I will create a grid primitive that will serve as our ground surface. At the end of the chain, I will add a null node with a clear name for organizational purposes. Now let's move to the second subcreate. Here we will create our procedural point cloud. I will use an object merge to reference the ground geometry we just created. Then I will use the scatter and align to generate a point across the surface. I will use density as the primary control and adjust a few settings to introduce some randomness. Also, add a null and name it outpt cloud. Now let's get back and create a camera. This will be our first node in the chain. Since we're already working in Solaris, the camera automatically becomes part of the USD stage and can be exported with the rest of the connected nodes. I will position it and adjust a few settings to get a more interesting perspective. Next, let's create some simple geometry that it will use for instancing. For this example, I will keep things simple and create a basic cube primitive. I will use a match size node to place it correctly on the ground. Add a normal node for better visualization. Next, we need to add an instancer node and connect our cube to the second input. And to reference our point cloud, we have to specify it inside the node. I will use an object merge to reference our point. Be sure to use display on the desired node which you want to be used in the output. We can always use a null or an output node for this purpose. Now at this point, we have already a complete USD scene consisting of environment geometry, a camera, a procedural point cloud, and instance geometry. Before moving on, let's merge and rename our nodes and organize the scene hierarchy so that everything remains easy to navigate once we move forward. Now let's export everything to USD and see what we get inside the Unreal Engine. I will use a USD ROP node, choose a location where I want to save the file, and press save to disk. Now let's go back to Unreal. Inside our USD stage actor, I will specify the path to the file we just exported. As soon as the stage loads, we can see that Unreal creates a USD asset folder and generates the necessary assets for the stage. We can also see that our hierarchy has been preserved. There is a camera actor, our environment, and the instancer, matching the structure we created inside Solaris. If I view the camera and compare it with Houdini, we can see that the framing and composition match perfectly. Now I want to pause for a moment and talk about this instance. You might be wondering why I was talking about PCG and attributes if USD itself is already capable of transferring instances, and for many workflows, that can be completely sufficient. However, once the data arrives through the instancer, it remains controlled by USD stage itself and limits our ability to take advantage of Unreal Engine's procedural ecosystem. Features like runtime generation, biome systems, gameplay integrations, filtering, asset variation, and many others. Another important advantage is performance and scene management. Unreal Engine can optimize, stream, and process PCG generated content much more efficiently, not to mention GPU execution. So, let's try transfer points and attributes and use them to rebuild the environment with PCG. Back in Houdini, inside the SOP create node containing our scattered points, I will create a raw Alembic output node and choose a location where I want to save the file. Now in our PCG graph, we assign this file. I will drag it on our level and press D for debug. And we can see the points appear. And they are tiny. This happens because Houdini and Unreal use different units. Houdini works in meters, while Unreal uses centimeters. To compensate for that difference, I will add a transform node and set it to uniform scale to 100. Resave the file and force a regen in PCG. The points are now much closer to the expected result, but the ground plane is oriented in the wrong direction. This happens for another reason. Houdini and Unreal use different coordinate systems. To fix this, I will apply a 90-degree rotation and regenerate once again. Now we can see that the points are positioned exactly where our USD instances are located. Let's add a static mesh spawner and assign a cube we created earlier. As you can see, the cubes appear much larger than we expected. This is because the scale of the geometry is automatically handled inside the USD workflow. If we inspect our original asset, we can see that the mesh itself is already quite large. One possible solution would be manually adjust transform inside the graph. However, I don't recommend doing this. The real advantage of this workflow comes from using attributes. So let's inspect them. With the node selected, I will press A to view the list of all attributes. We can see that our point cloud contains 12 points, and every point contains a number of attributes. The ones prefixed with a dollar sign belong to PCG itself, and they are often called as property. The attributes at the end, such as orient, p-scale, were transferred directly from Houdini. If we compare the values with the geometry spreadsheet inside Houdini, we can see that they match. Note, P attribute from Houdini, which is basically position of the points, is not visible as a custom attribute in PCG, because it uses the Alembic to generate those position points. So the P attribute in Houdini becomes $sign position in Unreal, while custom attributes such as p-scale, orient, tag, or any user-defined attributes remain available for procedural logic. You may also notice that some position values appear different. For example, here we have 45 on X and minus 59 on Y, while in Houdini we have 45 on X and positive 59 on Y. This is caused by the conversion scale adjustment that is enabled by default in the lower Alembic node. If we change it back to 1, we can see that the attribute values update and now match Houdini exactly. Now let's fix the scale of our cube. We can do it through mapping data between attributes using the attribute mapping section. I will add a new line and map our Houdini p-scale attribute to $scale, which actually controls the scale of our points in PCG. If we inspect the attributes again, we can see that p-scale is gone and its values have been transferred to $scale, affecting all three dimensions simultaneously. Now our cubes have the correct size, but they still don't match the position of our USD instances. If we inspect one of the instances from USD, we can see that it has position of positive 45 on X and negative 59 on Y. So, we need to find a reliable way to convert coordinate systems once and for all. I won't spend too much time explaining the mathematical details behind coordinate system conversion between these software. Instead, I will explain you a setup that works reliably in production, which I can use in the future no matter what software you use. The first important rule is to keep the conversion scale positive. As far as I know, Unreal Engine doesn't like negative scaling, and even if PCG does support it, it is generally better to avoid it. Instead, we can manipulate our attributes directly. Let's take our position attribute from Houdini and remap it to our point. It's not immediately obvious, but instead of using P, we need to type position. We want to map it to our PCG points $sign position attribute. And at the same time, we want to change the axis order. Look, we can do it by typing .xzy. This swaps two of the axes. This will immediately move everything back into the wrong orientation. Remember, earlier we added a 90-degree rotation to compensate for the coordinate mismatch. The rotation is no longer necessary. So let's go back into Houdini and disable it. I still don't want to modify the scale conversion, because units are not the same thing as axes. We could potentially change the conversion scale inside PCG, but this would affect not only position values, but also other attributes, such as scale in this example. So it's okay to keep our uniform scale at 100. Now everything matched perfectly. And what if we want to go one step further and assign every instance its own orientation? Back in Houdini, I will return to scatter and align, increase the maximum angle to 360 degrees, and add a little bit of incline. When I will export the Alembic again. Don't forget to export the USD as well, since we need something to compare against. Back in PCG, we now want to map our orient attribute to $sign rotation. If I map it directly to the rotation and also apply the XZY conversion, we will get an error. Why? Because orient is a 4-dimensional vector, or more specifically a quaternion, while rotation expects a 3-dimensional vector. To fix this, we can specify the correct type for the rotation attribute by adding W as a 4th dimension, and the error disappears. But be careful with this kind of conversions, as it can cause crashes. In this example, make sure the 4th component of the orient attribute is not 0. Now we have both position and rotation being transferred correctly, but the cubes still don't perfectly match the USD version. This means that even with the XZY axis flipping trick, we still haven't completely matched both coordinate systems. Thankfully, we can solve this using the built-in conversion flip-handedness toggle. As soon as we enable it, the cubes align perfectly with the USD instances. One important thing to remember is to apply XZY to the scale mapping for proper workflow, even though in our case p-scale is a float type. By the way, we built this completely from scratch. PCG actually ships with presets for these conversions. We can choose the city sample percent, and most of this setup is already configured for us. However, I wanted to show you the power of attributes. They are the foundation of the entire workflow. In this example, we use them primarily to solve the data conversion problems. But once you understand how to manipulate attributes, you gain complete control over your data, whether it's floats, vectors, strings, integer, or any custom metadata you want to transfer between applications. Now the next part will be managing instance variants with a single point cloud. I will go back to Houdini and create a variant attribute in our point. I will use an attribute randomize with custom discrete option and set it to constant values. The generated values are floats, but for this case we need integers, so we have to cast them. Now inside our scatter geo, let's create two more meshes, a head and a peak, for example. I will disable shaders for now and tweak their scale, copy match and size, and a normal node. We also need to specify a path for each primitive to get a proper USD hierarchy. Now, we can see that our scatter geo contains 3 child primitives. Back inside the instancer, we need to specify prototype index option as a custom index attribute and type variant. As you can see, it spawns all objects at once on a single point. To fix this, we need a collection. I will create one, give it a name, and specify the primitive we want to use. An asterisk sign means everything. Now, inside the instancer, I will reference the collection using the percentage sign followed by the collection name. And now we got a specific object spawned based on variant index on our points. Let's export this as USD and check it inside Unreal. Great, everything works, and we can see that Unreal also added these meshes in USD asset folder. Now let's figure out how to do the same thing in PCG. Before exporting the Alembic, I want to remove unnecessary attributes for optimization purposes. We can delete tag and normal. Now export and take a look at PCG. We can see that every point now contains a variant attribute. If we look at static mesh spawner, we can choose a mesh selector type option, and the one we need is select by attribute. So now, we have a point cloud that stores instructions, but PCG has no information about which mesh should be used for which variant index. One good way to explain how to do it, it is with a library analogy. Imagine a librarian who only knows which index number corresponds to a certain book in a library, and every book has its own name. Already we can say that he needs to process two types of information. In our case, as technical artist, that would be a string type with the name of the book and integer type with an index. So, every time PCG runs, each point will request a librarian with an index 0, 1, 2, etc. And he should return a certain book corresponding to that number. That book will then be transferred to the static mesh spawner, which will read the name of the book and spawn it on that point. If this sounds like some kind of mumbo jumbo, don't worry. Let's build it step by step and you will see exactly what I mean. First, let's define the types of parameters the librarian should operate with. For this, I will create a struct asset and create two variables. The first one will be book name, which is static mesh object reference. And the second is the integer, which is a book index. Next, let's create a librarian himself. This will be a primary data asset blueprint, and we need to provide him with this knowledge, so to speak. I will add a variable and reference our custom struct we just created. I will call it book storage. Now we can create a library and give this man some business to earn a dam. So we create a data asset based on our blueprint. We can see that we have only one option here. That's because we didn't set the type of the reference table used by the librarian. So let's change it to an array and make it visible. Now inside the data asset we can specify the exact number of books we want to place in our library. In our case it's just 3 variants. The book name attribute is for the path, or in other words string, to the static mesh located in our content browser, and the corresponding index. Okay, now that our library is officially open for business, let's see if our librarian can actually find the right books and justify his salary. To hire him, we need to create a job position inside the PCG. In the graph parameters, add the new one. This will allow a librarian to know which library he should work in. I will set its type to our blueprint and assign a data asset we just created. Let's call it DA library books. Now we can drag it in our graph. By default, it is just the exterior of our library, and I want to step inside. So I will use getProperty from object path. And we need to specify a property that the librarian should operate on, like a specific door we want to open. Its name is book storage. And now we have successfully accessed the data inside the library. Now the last step is to provide our points with access to that library and transfer all the books to the static mesh spawner node at the end of the stream. For this, there is a great node called match and set attributes. Into the first input we plug our points as if we entered the library themselves. Into the second input we plug our library structure. Now the points only have a variant attribute, which contains indices that need to match our book index, and that's exactly what we need to type in here. Now, every point acquires the book it requested. You can see the corresponding book name to the certain variant attribute. Lastly, in the static mesh spawner, we simply specify the attribute to read from points, and in our case it's book name. Voila, we have everything working smoothly, and a librarian can finally get his payment to make a living. Hopefully. This is exactly the way I created this environment, and the sky is the limit. You can see me doing all the procedural magic in Houdini with the ground plane. With only 2 files, I transfer all this into Unreal Engine and turn it into a beautiful image. This is a basic implementation tool, but a very powerful way of working in non-destructive workflow. You just need to think carefully about your scene and define beforehand what would be instanced on points and what should remain as static geometry. And the best part of this pipeline is that it's easy to combine the work of multiple artists, since everything is unified through a modern way of representing data with USD. Before the finish, I also want to mention an amazing project by Adrian Pan. I came across his work while exploring more advanced procedural workflows. Unlike the workflow we build today, his setup doesn't rely on exchanging files between applications. Everything is transferred through a live connection using Houdini Engine. I really want you to see how powerful this workflow can become beyond this basic example. The best part is that he has made all these resources completely free. So, if you're interested, definitely check out his YouTube channel and GitHub. It's a fantastic project, an excellent resource for learning more advanced procedural workflows. This is all for today. I hope you understand why this is such a unique approach. I have attached the links with the additional information with the great Houdini and Unreal Engine tutorials and docs if you would like to dig deeper. There is also a great instructor, Adrian Logut, who built his YouTube channel specifically around explaining PCG. If you have any questions, please leave them in the comments. I will try to do my best to answer them. Thank you and take care.